The Lagrangian, a deep perspective on motion. The Lagrangian is a function that describes the dynamics of a system. It provides a powerful way to predict how a physical system evolves over time, using the principle of least action. In simple terms, instead of solving Newton's force-based equations, the Lagrangian approach finds the path a system takes by minimizing, or extremizing, a quantity called the action. Historical development. Why did we need the Lagrangian? Before the Lagrangian was introduced, physics was mainly described using Newton's laws of motion, which are force-based equations. But Newtonian mechanics had limitations, particularly for complex systems like systems with constraints, e.g., a pendulum attached to a moving cart. Motion in generalized coordinates, e.g., planetary orbits. Classical field theories, e.g., electromagnetism. 1. Origins, Fermat's principle, 1600s. The idea behind the Lagrangian can be traced back to Fermat's principle of least time, which states that light takes the path that minimizes travel time. This hinted at a variational approach to physics, where nature follows optimal paths. 2. Maupertuis' principle of least action, 1700s. Pierre-Louis Maupertuis extended this idea to mechanics, proposing that physical systems follow paths that minimize an abstract quantity called action. However, his ideas were vague and lacked a precise mathematical formulation. 3. Euler and Lagrange, 1700s, formalization of variational calculus. Joseph Louis Lagrange, 1736 to 1813, built on Euler's calculus of variations to formalize Lagrangian mechanics. Instead of focusing on forces, Lagrange formulated mechanics using generalized coordinates, which describe motion more flexibly than Newton's Cartesian approach. What is the Lagrangian? The Lagrangian function is defined as L equals T minus V, where T is the kinetic energy of the system, V is the potential energy of the system. Instead of tracking forces, the Lagrangian method determines how a system evolves by using the principle of least action. S equals indefinite integral L dt. The system follows the path that minimizes the action S. In words, the action S minimizes the total sum of the difference between kinetic and potential energy over time. Mathematically, S equals indefinite integral L dt equals indefinite integral T minus V dt, where T is kinetic energy, energy of motion. V is potential energy, stored energy, like gravity or a stretched spring. L equals T minus V is the Lagrangian, which varies over time. The system follows the path that makes S as small as possible, or sometimes stationary, meaning it could be a minimum, maximum, or saddle point. Intuitive explanation. Imagine you're throwing a ball. The path the ball follows, a parabola, isn't random. It's the one that minimizes the total action. If the kinetic energy is too high, the action is large. If the potential energy is too high, the action is also large. Nature balances both, finding the best path where the difference T minus V is optimal over time. So the principle of least action says, of all possible paths, nature picks the one where the difference between kinetic and potential energy varies in the most efficient way over time. Historical development. Why did we need the Lagrangian? Before the Lagrangian was introduced, physics was mainly described using Newton's laws of motion, which are force-based equations. But Newtonian mechanics had limitations, particularly for complex systems like systems with constraints, e.g., a pendulum attached to a moving cart. Motion in generalized coordinates, e.g., planetary orbits. Classical field theories, e.g., electromagnetism. What problems did the Lagrangian solve? 1. Handling constraints easily. Newton's approach required complex force equations when dealing with constraints, e.g., a bead sliding on a curved wire. Lagrangian mechanics allowed physicists to describe motion using generalized coordinates, making the equations much simpler. Example: a double pendulum, a pendulum attached to another pendulum, is chaotic and hard to analyze with Newtonian forces. Lagrangian mechanics makes the problem easier by describing it in terms of angles instead of forces. 2. Natural fit for generalized coordinates. Newtonian mechanics works best with Cartesian coordinates x, y, z. Many problems, like rotating systems, are better described using polar or spherical coordinates. The Lagrangian automatically adapts to any coordinate system, making it highly versatile. 3. Derived the equations of motion systematically. Newton's laws required direct force analysis for each case, whereas the Euler-Lagrange equation provided a systematic way to derive equations of motion, where Q represents generalized coordinates. 4. Led to Noether's theorem, symmetry and conservation laws. Lagrangian mechanics allowed Emmy Noether to prove that symmetries correspond to conserved quantities, e.g., time translation symmetry energy conservation. This was a revolutionary insight in physics. 5. Essential for modern physics, relativity and quantum mechanics. Hamiltonian mechanics, a reformulation of Lagrangian mechanics, became central to quantum mechanics. Einstein's general relativity was developed using a Lagrangian approach for describing spacetime curvature. Quantum field theory, QFT, describes fundamental particles using Lagrangians. Conclusion: why the Lagrangian matters. The Lagrangian reformulated mechanics in a way that simplified complex systems, made conservation laws emerge naturally, extended to modern physics, including relativity and quantum mechanics. It transformed our understanding of motion, from Newton's force-based view to a deeper principle of least action, which applies across all of physics.